Saxon's Calculus Lesson 56 is about related rate problems. So now they're trying to give you some real-world applications for how we can deal with the derivatives or integration, mostly derivatives, that you know how to do at this point. So I went ahead and started the sketch for example 1. It says that I have a 13-meter long ladder that is leaning against a vertical wall. The base of the ladder is pulled away from the wall at a rate of 1 meter per second. And it wants to find the rate of how the top of the ladder is falling. And the base of the ladder is 5 meters away from the start. Now, all I have is this sketch at this point. I have no equation, but I do know that if I have a wall, that this is a 90-degree angle, therefore this is a right triangle. So I can stop and find that this height would be, 13 is the hypotenuse, so 169 equals 25 plus, we'll call it our y squared. Then y squared equals 40 or 39, hang on. For some reason, I can't do that in my head. 144. Okay, so then y is 12 meters to match everything else. All right, now that I have that, I need to still work on the equation of how things are changing. So again, if I call this one x and I call this one y, and I write that out in an actual equation, x squared plus y squared equals the 13 squared. And I'm going to go ahead and write that then as the 169. This is an equation that I can actually derive. So this would go to 2x plus 2y equals 0. Oh, and I should have with this one dx and I should have with this one dy because I'm looking for that rate of change so that I can use this. So that needs to be solving for dy over top of something. And because we're dealing with, here's my clue here, time, what I actually want to be solving for is dy over dt. So they're both over time because I need time in this equation. So now to solve for dy over dt, we're going to have negative 2x, I was going to put it over 1, but I'm not, dx over dt. So we have our, wait a second. No, I'm not finished. I moved the 2x over, making it minus, I didn't divide by 2. Yeah, okay, yes. So, oh, good grief. I'm solving dy over dt. This is dividing by 2y. Oh, dy over dt equals negative x over y. Now I feel like I'm getting there. Dx over dt. Okay, so here's our derived formula. Now, we just found that our original x was 5 and we found our y to be 12. So we're filling in here dy over dt equals negative 5 over the 12 multiplying with dx dt. Well, what was that dx dt? That was the rate that the x was changing, which was in 1 meter per second. So then when we simplify that, we're going to get negative 5/12, and that is still in meters per second because the multiplying by 1 did not really change anything. Now I'm going to pause it again while I graph example 2. Okay, so we have a 6-foot-tall man walking away from a 15-foot street light. At what rate is his shadow lengthening when he is 20 feet away from the street light? And he's walking away at a rate of 4 feet per second. Now again, I don't have an equation here, and this time rather than solving for the missing parts, I'm going to go ahead and focus on the equation that we need to be deriving. So as you should recall, I have a large triangle here that has a 15 for this side and then a 20 plus an extra piece here. And I have a little triangle here created by the man with this side being 6 and this side being that same unknown whatever. So if I set them up as a proportion, I'm comparing 15 to 6 from the big one with from the other one, and I'm going to call, even though I know that's 20, that's part of the numbers that I need. And this is where these problems are not necessarily intuitive. So this one is an X, and we'll call this one L just to match what they're doing. So X plus L is comparing with the L from the small one. Now to cross multiply that, I would get 15L equals 6X plus 6L. Are they putting their L? Yes. Okay, so put the L's together. That's going to be, I want to make sure I'm not skipping to their derive. Yeah, I am solving. My first instinct was right. So I want to solve for the X by putting the L's together. So that's going to be 9L dividing by 6 equals the X, and then reduce that down to X equals 3L over 2. Yes, now I have an equation that I can derive. So this this X goes to dx, and again, because I'm dealing with time, over dt equals, and then my 3/2 acted as my coefficient. L, the 1 is going to multiply by that and then drop off, and then that was dl over dt because I derived the L. Okay, then I need to solve for the rate of change dl, yes, okay, dl over dt needs to be solved. This needs to be isolated. Okay, so that means the 3/2 is dividing, so flipping. So dl over dt equals 2/3 with that dx over dt. And we know that the dx over dt is the 4, so I can plug the 4 feet per second in here, creating the 8/3 feet per second. Yes. And since that's all they wanted me to find was how long that was lengthening, that was my other clue that I needed to solve for the X so I could get the DL piece was here. Like I said, these are sometimes just not instinctively intuitive. Now, example 3. Pause again while I grab. All right, so forgot to move my notebook back. So for example 3, it says we have a conical container that has a height of 9 centimeters and a diameter of 6 centimeters. It is leaking water at the rate of 1 cubic meter per minute, and it wants us to find the rate at which the water, which they're calling level H, is dropping when eventually we're going to plug in H is 3 centimeters. So I knew that I was dealing with volume of the water because that's what's leaking out. And so the volume of a cone is the area of the circle, pi times radius squared, times the height of the whole thing. And then because it's a cone, it's multiplied by 1/3. Now, before I finish dealing with this one, I know I need to do the comparison of the given parts. So because I have radius here in the equation, I need to deal with radiuses. So this radius is 3. 3 is going to compare with an unknown radius down here. So let's call it R. And then from the large one, that was comparing with the 9, and then the H that's spilling out. Then solve for the rate for the small one. That's going to be 3h divided by 9, and then that's going to reduce down to h over 3. Now I know what the radius of this one is. I can plug it in with our volume formula. So we have our pi times our h over 3 squared times our unknown height times the third. And simplify. That will be, pi is considered a constant, so is that 1/3 at this point. So at the moment I have let's just put pi over 3 multiplying with h squared over 3 squared is 9, and we still have the h. So now pi over, pi h cubed technically, because h squared times h is h cubed, and then 3 times 9 is 27. So basically pi over 27 is my constant and h to the third is my variable. Okay, so now that is what my volume equals. Okay, so we can derive. So dV, and that should imply over time, yes, equals, okay, so now pi over 27 is the constant that's going to multiply with the 3h squared, and what was I deriving there? H, so dH over dt. And I can simplify here, dV over dt equals pi h squared, and then the 3, so 9. So pi over 9 is my constant with the h squared, and we still have that dH over dt. Now, it's dropping, so I need to be solving for dH over dt. Yes, okay, so now this is going to divide, it's going to flip, so we're going to get 9 over the pi h, just a second, that h squared was in the top, so let's write 9 over pi h squared, and then that is our dV over dt equals the dH over dt. Now, our dV over dt was 1 meter cubed per minute, so the 1 isn't going to change anything. So that's going to keep it at 9 over pi with our h. And I know I'm going to substitute something in there in just a second. And we've already multiplied by the 1, which didn't matter. So I need my meters cubed per minute. And now, what did it tell me to plug in? It wanted me to test h at 3. So we're going to fill 3 in here. 3 squared is 9. And so they're going to cancel off. And that basically leaves me 1 over pi. And I failed to do one thing. It was leaking out, which means it's at a minus. They didn't tell me that, but it is implied. So this should be at a minus once I've done that multiply. So that gives me negative 1 over pi, which I would do on my calculator to get it accurate, or you can do the 2.7. But either way, you're turning it into a decimal, negative 0.32 meters cubed per minute. Oh, yes, they had, just a second. Let me make sure they didn't do another convert. They have centimeters per second, not centimeters cubed. Check on your calculator and see if that actually gives you the negative 0.32 meters cubed per minute, or whether that is a conversion. Like this may give you a different decimal and then they converted it. If that's the case, I would stick with whatever -1 divided by pi is as the decimal and meters cubed per minute, because it doesn't say I have to do it, does it? Just a second, let me reread that and make sure. Leaking water, find the rate at which the water is dropping. No, it does not. I would definitely leave my answer in meters cubed per minute. I'm not going to box it because I'm not 100% sure that that is the accurate number.